Now let's talk a little bit about the famous Hubble law of expansion of the universe. There we go. I kind of spelled beans here without actually explaining what's going on here. So the thing is, astronomers had known since 1910, astronomers knew that spectra of most spiral galaxies tended to be redshifted. Spiral galaxies are red shifted. All right, kind of like here. You take a spectrum, you spread the light from the galaxy, and you see these absorption features, absorption lines or features, and they're expected to be at a certain wavelength, but they are observed shifted. You see? They're shifted towards longer, therefore redder wavelengths. This is what we have on the x-axis, okay? And that happens for all of the features, all of them. And they're important features, and we are able to identify them. And we know exactly why those wavelengths are there, like in the laboratories. So this is, galaxy at rest. And this is the red shifted galaxy. So recall that redshifts occur when the object emitting the radiation is moving away from us, right? So basically, because the spectral features are redshifted, that means those galaxies are moving away from us. Now, following Hubble's discovery of the Cepheid variables in the Andromeda, and therefore upon calculating the distance to Andromeda and finding out that it's just so far away that it cannot be just something, a blob of gas or something that's part of our own Milky Way, and so it is a separate thing and maybe something like the Milky Way, so basically another galaxy. Hubble and his co-workers spent the next few years busily measuring the redshifts of galaxies and estimating their distances, okay, from the Cepheid variables. Okay, so he started to measure distances and found that the redshift and distance, they were measured independently. They are related in a special way. And here is the way, right? So what do we have? Basically, the recessional velocity, and that's coming from the redshift. And the distance, that's from Cepheid variables mostly. And the dots are measurements for individual galaxies. And there weren't very many, but it was becoming pretty clear that there is a linear relation, right, between the velocity at which those galaxies are moving away from us, and the distance. And that line, right, linear relationship, that had a slope, and that could have been calculated, and that was called h naught. And this is called the Hubble constant. And it is a constant because that is basically true for every one of those galaxies, right? So that says h naught is basically what we have on the y-axis, right? The slope, it's the tangent of that angle, theta, okay? The slope, and that's called h naught. That is going to be basically the recessional velocity divided by distance, or this relationship, which is called the Hubble law. It could have been Hubble and Humason law because they actually worked together, but somehow Hubble's name stuck much better with this relationship than just Hubble and Humason relationship or law. Okay, so the value of the Hubble constant is 22 kilometers per second per mega light year. So 1 mega light year is 10 to the 6, that is a million light year. So basically what this law says is that galaxies move away from us that is Milky Way, basically, at a speed of 22 kilometers per second for every million light year distance. Right, so this is basically the meaning of this Hubble law. Okay, so galaxies are moving away from us. Actually, galaxies are moving away from one another, if you want. At a speed of 22 kilometers per second for every million light year distance, which is pretty cool, okay? And so the Hubble flow is actually seen by all galaxies. The universe has no center and no edge. Everywhere you would try to measure this Hubble flow, this redshifting of galaxies away from one another, is going to look the same as far as we can tell. So for example, look at if you measure the Hubble flow from the perspective of galaxy A, you see all the other ones, all the other galaxies moving away from it. But in the case somebody from galaxy B is measuring the Hubble flow, then again is seeing that all the other galaxies, including galaxy A, that we have been from the perspective of which we have discussed the Hubble flow previously, is also moving away from the B. So it's actually, everywhere we look, we see the same thing, okay? And basically, a distance becomes a look back time, okay? Actually, distances themselves become something rather tricky to measure, even though now by Hubble's law we are now able to measure distances, right? So Hubble law that said distance is velocity, the recessional velocity, divided by that constant, the Hubble constant, right? So basically we got a new way of measuring distances. But again, that's tricky we need to know the exact value of this constant, right? And we get the velocity from the spectra from measuring redshifts. So pretty neat. Now, astronomers measured many of these redshifts and many of the recessional velocities and distances, and they were able to, at some point, formulate a principle, a cosmological principle that said on large scales the universe looks about the same no matter where you are within it. Okay, so in other words, the matter is evenly distributed on very large scales, so not in the minutiae of exactly where inside the galaxies things are or where the spiral arms are. Just on a very large scale, the matter, that is the galaxies, the luminous matter especially, is evenly distributed on very large scale in the universe, and that we are not able to find a center or an edge to this universe. Now, this is something rather interesting. This is called a principle because these ideas actually are not proved, but they are consistent with all of the observations today. And something even more interesting is that all these distance measurements actually, especially those obtained with or from Hubble's law, tell us the age of the universe. So basically, for how long were these galaxies moving away from one another? Now, that be? Well, first of all, a few words about the distances between the faraway galaxies. Those distances actually change while light travels, right? Because it's, that speed of light, 3 times 10 to the 8 meters per second. It is large, but finite. All right? So it's not infinitely large, so it is going to take time for light to travel. And take this example here of a supernova exploding in a galaxy that is, located at this distance, about 400 million years ago, right? And we are going to basically see it today because it's going to take 400 million years to arrive at us. Okay, so this is Milky Way today. But in the meantime, this galaxy, the host of that supernova, traveled some more, so now it is at larger distance than it was when the supernova exploded. So you see, astronomers actually end up thinking much better in terms of look back time, like you remember that 400 million years ago, rather than distance, right? Because this distance is definitely not the same as that, right? So it was a certain distance in between that galaxy hosting the supernova and us, the Milky Way, when the supernova exploded, and then there is a different distance now when we finally get to see the light that was emitted by that supernova 400 million years ago. So basically, because of this look back time, right, what we actually get to measure is, at the end, the age of the universe, because that Hubble's constant relates velocities and distances for all of the galaxies. And so this relationship is true for all galaxies. All things in this universe that are at large distances away from one another. And so remember that Hubble law that said distance again is velocity divided by Hubble's constant. Now turn it around and just solve for 1 over h naught. That is velocity divided by distance. And that is actually the inverse of time. Remember? Time, distance, divide by speed or velocity. Okay? And so velocity divide by distance, right? This is inverse of some sort of time. Well, what time would that be? It's all of the time that that distance that we measure has been traveled, right, at the speed at which those galaxies travel. And that is going to be basically the age of the universe. And that is 1 over h naught. One way to do it again. Okay, so distance divided by velocity, and this is 1 over h naught. Basically, the inverse of the Hubble constant is the age of the universe. And I'm going to make a little parenthesis here and tell you that, hey, we can actually kind of calculate or estimate the size of the universe, or maybe not the universe per se, but the cosmological horizon. Basically what we are able to see thanks to light carrying the information, or basically the maximum look back time of 14 billion years. That is the inverse of the Hubble constant. So what would the size of the universe be? Say the radius, the Hubble radius. Well, that looks like a distance, so it's going to be speed of light times the Hubble time. And so we get c over h naught. So go ahead and calculate that, see what you get. And you got a good estimate about how big the universe is.